Welcome to this lecture for statistics. Today we're talking about using correlations. So, correlations, what are they for? Well, they're for measuring and describing a relationship between two variables. So there's three aspects of the relationship that correlations typically look at. One being the direction of the relationship. The direction can be either positive or negative. When there's a positive relationship between two variables, that means that they covary in the same direction. Right? So that means that higher scores on one variable are associated with higher scores on the other. And conversely, lower scores on one variable are associated with lower scores on the other variable. Right? People sometimes get confused when they see positive and they think, oh, that means high and high. But low and low, no, that's negative because low is negative. Nope. Positive just means that in the same direction. As one goes up, the other one goes up. As one goes down, the other one goes down. If you think about, remember back to your days in geometry, the slope of a line, same kind of thinking applies here. When you have a positive slope, it increases as x gets bigger, y gets bigger. With a negative slope, as x gets bigger, y gets smaller. So things go in the opposite direction for negative relationships. So for negative relationships, they covary in opposite directions. Higher scores on one are associated with lower scores on the other, and vice versa. Lower scores on that first one are associated with higher scores on the second one. So if you think about the correlation between study time and grade on an exam, would you think that would be a positive or negative correlation? Okay. So, okay, people that studied very little, people that studied less, the less people studied, the worse they tended to do on an exam. So lower on one, lower on the other. If that's the case, then that is a positive correlation, right? They're covarying in the same direction. What about the relation between number of beers consumed while studying and grade on the exam? So we said, okay, people that consumed more beers scored worse in the exam, and people that drank fewer beers scored better on the exam. Okay, those things are going in opposite directions, so that is a negative correlation. So, three aspects. One is direction, and the relations you look at with correlations are either typically linear or curvilinear. Most commonly, when we're doing correlational analyses, we're looking for linear relationships, right, where you have kind of this geometric progression. Change in one is related to a set amount of change in the other, where the amount of change doesn't change. There's not an acceleration of change. But there are some special correlation coefficients that can deal with curvilinear relationships, and there are some interesting curvilinear relationships in behavioral sciences, right? The most well cited one in stats classes is that anxiety performance relationship, right? Low levels of anxiety, you have low performance. As anxiety goes up, performance tends to go up as well, right? Because the more anxious you are, the more you're going to maybe study, the more serious you're going to take things, the more you're going to pay attention. So you're seeing kind of this positive correlation between the two variables up to a point, right? And then at some point, as anxiety gets higher and higher, performance starts to come down, where at the highest levels of anxiety, you may see back to the lowest levels of performance, where you had a positive slope and then a negative slope, suggesting that it wasn't a linear relationship, but a curvilinear relationship. And the curve can be that kind of inverted U, can be a regular U, or it could be more of a kind of exponential thing where the relationship is fairly flat and then gets steeper and steeper as you move out into more extreme values of X. But again, for the most part, we'll be looking at linear relationships. And then the third aspect the correlations look at are the strength or consistency of the relationship between variables. And typically we'll look at things, these coefficients range from 0 being weak to plus or minus 1 being strong, where a correlation of -1 is equally as strong as a correlation of +1. That sign, the positive or negative, is simply an indicator of direction, not an indicator of strength. Strength is, well, how far is it from 0? So think about absolute value of a correlation coefficient being an indicator of how strong the relationship is, how consistent that relationship is. Okay, so let's look at some relationships. This first one, we've got our x-axis and our y-axis, and we got all these observations here lined up, looking pretty much like a line. They're pretty close to some of that. If you drew some imaginary line trying to connect those dots wouldn't be too far from a line. So it's pretty linear. They're close to the line, suggesting it's a strong correlation, right? The more line-like the pattern appears to be, you know that's a stronger correlation. Would you think this is positive or negative? Right? So if we go from the corner in this thing is 0 on x and 0 on y, as we go to the right on x, as x gets bigger, what happens to y? Well, for low values of x, y was high. As x gets bigger, y gets smaller. So this is a negative correlation, a strong negative correlation. Okay. What about the second one? It's kind of this blobby thing, right? Trying to figure out, okay, well, if you try to fit a line in there, kind of a line that best accounted for all those points, it's not real clear if that line would go bottom to top, or top to bottom, or flat, or up and down. Like there's no clear line. Those are very blobby. So that would be probably pretty close to a zero correlation, right? And you can see at low values of x, there are some low values of y, some medium values of y, and some high values of y. So there's not this kind of consistent relationship between changes in x and changes in y if you have all kinds of values of y at one value of x. And as I go to the right on x, yep, some are high, some are low, some are high, some are low. There's not a consistent change in y as I change in x. Okay, look at this next one. A little bit more line-like than the previous one, not as much as the first one. So maybe not as strong a correlation as the first graph we looked at, but still a pretty decent correlation here. It's got a fairly linear trend. And this trend where you have low values of x, so fairly low values of y, and as you move to the right with larger values of x, you tend to have also larger values of y, suggesting that it's a positive correlation. Okay, one more. So this one looks like a line. Oh, that's very linear, very line-like. So you may be thinking, okay, this looks like a strong correlation. But look more closely. What's happening when you change in x? What's the associated change in y? For low values of x, we have this kind of moderate values of y. And as we increase in x, y doesn't change, right? So there's not any kind of predictable change in y. There's no change in y. And whenever there's no change in one of the variables, there's no correlation. So any kind of horizontal line or even a vertical line, if everybody had the same value of x, and for that same value of x, there were different values of y, well, that suggests those two variables aren't correlated. They aren't related, where changes in one would reliably predict changes in the other. Okay, so the particular correlation coefficient we'll spend the most time focusing on is the Pearson correlation coefficient, and there are several coefficients, but this is the most commonly used one, and the formula we learn for this can actually be used for some other coefficients as well. I think it'll tell you the degree and direction of a linear relationship between two continuous variables. That's what it's made for. It ranges in value from -1 to +1, 0 in the middle. And so if you have a perfect correlation, a correlation of 1.0 or -1.0, that means that every change in x, that's delta x, every change in x corresponds to a predictable change in y, right? So if x is 1 and y is 4, you got this point 1, 4. If I go to the right one on x, I go to 2, and y goes up 2 to 6. So go from 1, 4 to 2, 6. So a change in x of 1 corresponding to a change in y of 2. Well, if this is a perfect correlation, then I know, well, once I go to x equals 3, y is going to be 8. It's going to, because again, a change in x of 1 is a change in y of 2. And I can go beyond that and say, oh, well, if I go up to x equals 10, that's going to be y equals 22, right? Because there's a formula for that line that I can, if I have enough points, I can figure out. And now I can figure out for any given value of x, I can predict what y is going to be because there's this predictable rate of change. Right? There's this ratio. It's like the slope of a line. And the closer a correlation is to 1, the closer the observations are to this kind of theoretical formula for a line. So that Pearson R really is a ratio. It's a ratio of covariability between X and Y relative to the separate variability in X and Y. So how much do X and Y covary? So high values of X and high values of Y, okay, they're covarying together. That's high covariability. If, well, when X is high, Y is sometimes low, but Y is sometimes high, okay, they're not covarying very much. They're going in opposite directions. And we'll see this more closely in a minute, I think. And then the separate variability is just look kind of your sums of squares in each one. How much variability is there in your X values? How much variability is there in your Y values overall? So that formula looks like this. We have R equals SP over the square root of sum of squares X, sum of squares Y, where SP is your sum of the products, which is really kind of just a sums of squares of variability. So you've got a ratio of sums of squares to another measure of sums of squares, right? Because if you've got sums of squares times sums of squares, it's basically a sums of squares squared, taking the square root of it to bring it back down to a sums of squares. So it's a ratio of variability, right? Where when all the variability in X and Y can be accounted for by the relationship together, that's a perfect correlation. And if there's all kinds of variability in the scores, but none of it is covariability, well, the numerator is going to be 0, and your R is going to be 0, or at least really, really small. Okay, so let's look at maybe something that helped make that covariability concept make a little more sense. So the covariability between X and Y, the numerator in that correlation coefficient formula, is the sum of products. So the definitional formula for sum of products is this: SP equals the summation of X minus the mean of X times Y minus the mean of Y. That's why it's the sum of products, the product of these deviations. When X is different from the mean, its corresponding Y, right? Because every X has a corresponding Y. You think about these coordinates, is that Y has some deviation from the mean as well. So if when X is above the mean, Y is always above the mean as well. And when X is below the mean, Y is always below the mean as well. Okay, then you're going to have, X minus the mean is a positive when it's above. Whenever you have that, Y minus the mean, the Y is above as well. That's a positive. Positive times positive is a positive. So I'm going to add that. And then when X is below the mean, okay, now it's a negative. But Y is also going to be below the mean in those times. That's also negative. Negative times negative is a positive as well. So when that happens, those things are covarying. High X's are with high Y's, low X's with low Y's. That SP, that sum of products, is going to be a large number, right? And it's going to be a large positive number. Now, if X and Y covary, again, consistently, but in opposite directions, where, okay, when X is above the mean, Y is always below the mean. And when Y is below the mean, X is always above the mean. Okay, you're always going to have a positive times a negative, which will give you a negative, which will give you, you're going to add up a whole bunch of negative products, giving you a large SP that's negative. But when X is above the mean and Y is sometimes above, sometimes below its mean, when X is below its mean, Y is sometimes above, sometimes below, you're going to have some positive products, some negative products, and they're going to wash out, and the SP is going to get closer to 0, right? So much like the sums of squares formula, the definitional formula maybe help us understand what's going on, but it can be kind of a pain to calculate because you're doing a lot of subtracting and multiplying there. So fortunately, I have a computational formula, which should look fairly familiar. Sum of the xy's minus sum of the x's times sum of the y's divided by n, where n is a number of pairs of scores, right? So let's look at some numbers. We've got these X and Y scores, 2, 4, 12, 8, 6, 4, 10, 1, 10, 8. You got their means, 8 and 5. So calculate the deviations for these. For that first pair, 2 and 4, for that person, their X was below the average of the X's, and their Y was below the average of Y's. Okay, so they're on the same side. And the next person, okay, well, they were above average on X and above average on Y. So again, on the same side. and then the next person below and below, and then we have this one weirdo who they were above the average for X but below the average on Y, and then we get back to our pattern of above and above. And if you look to the right column, you see the products. Okay, when people were above, below, below, you end up with positive product, positive product, positive product, and that one weirdo who is discordant gets a negative product. Whereas if they had all been positive, that SP would be even bigger. Like one person bucking the trend pulls it down a little bit, but not enough maybe to make it to take away from our significant correlation. But again, the more that product either becomes big positive or big negative, the more likely you are to have a significant correlation. It all has to do with, okay, are the X and the Y consistently on the same side of their respective averages? Above, above, and below, below, or above, below, below, above. Okay, looking at these same numbers, running all the way through a calculation here using the computational formula. So you set it up like you would when you're trying to get sums of squares, because you need sums of squares X and sums of squares Y. So you get your X scores, your Y scores, you sum the X's, you square all the X values, you square all the Y values, and you sum those. So you got some of the X's and some of the X squareds, some of the Y's, some of the Y squareds, and then this far right, we have this other column, X, Y. So that's each X value times its Y partner. So 2 times 4 is 8, 12 times 8 is 96, and then you sum those, sigma X, Y. Right? And once I do that, I've got all the pieces I need to calculate my R, right? Because for sums of squares X, that's just sum of the X squareds minus sum of the X squared divided by N. Same thing for Y. And then some of the products, it's sum of the XYs, that 218, minus sum of the X's, the 40, times sum of the Y's, 25, divided by N, again, where N is the number of pairs of scores. And I get 18. And that's the same value I got for some of the products using the definition formula on the previous slide. Right? So then the R value is calculated where you put the sum of the products in the numerator and divide by the square root of sum of squares X times sum of squares Y. And both those numbers are under the radical, didn't really show up here, giving us a correlation of 0.4. Right? So a positive correlation, which we knew as soon as we saw our sum of the products was positive, right? Because that denominator is a square root, so it's never going to come out negative. So whether it's a positive or negative correlation is always going to be determined by the sum of the products, which should make sense. And that's a moderately sized correlation, again, depending on what we're looking at. We may be like, oh, yay, or maybe, oh, crap. Because if a correlation is big or small, it depends on what we're talking about, which we'll see more about in a minute. Okay, z-scores. All this talk about scores being above or below the mean should kind of remind you of z-scores, because that's what z-scores are all about. Right? They tell you if a score is above or below the mean and how far it is above or below the mean. Right? That's all a z-score is. It's number of standard deviations a score is above or below its mean. So the interesting thing about z-scores with correlations is if you standardize all the scores in a data set, you can rewrite the Pearson formula to be a bit simpler. So if you happen to be given z-scores, it makes calculating correlation pretty easy. For a sample, R is then equal to the sum of z sub x times z sub y. So for every pair of scores, right, you had a pair of scores that was 4, 6. Okay, now they've been standardized as z-scores. So that z-score may be 1.1 and 1.3. Multiply those two together, get another pair, multiply those z's, get another pair, multiply those z's, add all those up. That'll be your numerator, divided by n minus 1, where n is the number of pairs of scores, and that will also give you your correlation coefficient. Which again, when you're summing up these z's, if you have a strong correlation, a strong positive correlation, you're going to have z's that are positive z's for x associated with positive z's for y. Above x, that's above the mean, right? And you're going to have negative z's for x below the mean associated with negative z's for y, below the mean, right? And the more consistent that is, the bigger that numerator is going to be, the larger you're going to get for a correlation on the output. And if you have the entire population scores, same thing, you just change it to row. It's that kind of thing that looks like a little squiggly P. That's the parameter for correlation. Okay, using and interpreting Pearson correlations. Used for a couple things. One, used for prediction. Right? When you have really strong correlations between variables, that allows for prediction of outcomes given certain values of a predictor. If two things are highly correlated, if I know, okay, well, if GRE scores were highly correlated with graduate school GPAs, okay, that means I could look at people's GRE scores and make some predictions about how well they're going to do in graduate school. Right? And just FYI, there's not a strong correlation. Validity. Correlations are often used to establish the validity of measures. So when we're talking about convergent validity and criterion validity, if I've got maybe a new measure that I created of depression, and I want to say that it has good convergent validity, okay, then I need to show that I'll give people my measure of depression, and then I'll give them some other established measure of depression. And if my measure is measuring what it's supposed to measure, well, then it should converge. It should correlate with other measures of depression. So if I have a high correlation there, with that, I'm probably looking for R of 0.7 and above. Right? That's good convergent validity. Criterion validity is similar. My measure of depression, rather than seeing if it's correlated with another measure of depression, criterion validity says, does my measure correlate with some outcome? Right? So I've been giving people my measure of depression, and then they were tracked for maybe hospital admission. And if my measure of depression predicted admission to the hospital for suicidal ideation, okay, then that's an indicator of good criterion validity. And for that, I'm probably looking for a lower correlation, significant, but maybe 0.3, 0.4, because there's lots of other variables that are going to impact whether somebody presents to the hospital. And there's some variability in depression, right? Mildly depressed, you're probably not going to present, so it's going to take a while. It's going to be on the higher end until we see that triggering that criterion, that outcome. Related to that, also correlations often used and cited to establish the reliability of a measure. Primarily when talking about retest reliability. So if this measure is reliable, the score you get today should be the score you get next week if you take the measure again. And for that, we're looking for correlations, around 0.8, 0.9, assuming a fairly small amount of time. If we're talking about a year, okay, maybe not so big, but a week, yeah, should be super high correlation if it's the same test. Theory verification. Obviously, theories often predict relations between variables. So if this is true, then these things should be related. So now we can go through and do surveys, gather data without having to manipulate variables, and we can test theories with correlational analysis. What about causation? Can you establish causation by showing that variables are correlated? So smoking is correlated with lung cancer. Therefore, smoking causes lung cancer. Well, it does, but you can't infer causation from correlation, right? And two primary reasons, the problem of directionality and the third variable problem. The direction problem is whenever two things are correlated, there might be a causal relationship, but you don't necessarily know which way the causal arrow runs. So anxiety and depression, fairly highly correlated in clinical populations. But does anxiety cause depression? Or does depression cause anxiety? And the clinical answer is both. It's a bidirectional relationship, but you can't tell that from a correlational study. That's why you need experiments to really look at issues of causation. And then the third variable problem is when two variables are related, it could be that there's not a causal relationship at all, but that there's some third thing that, A and C are related because A causes B and B causes C, or they have something in common. So if there's a strong correlation between number of ashtrays in your home and likelihood of lung cancer. So ashtrays cause lung cancer. Well, no, but people who smoke more are going to have more ashtrays, and people who smoke more are going to have more lung cancer because it does kill you. Don't smoke. So you can't infer causation from correlation. But it's a possibility. If correlation is there, that means there might be a causal relationship. And that's how a lot of research is done, because experiments are often expensive and time consuming. And if you're not sure that you're going to find something, you probably don't want to ask the question first with a big, expensive, fancy experiment. You want to ask the question first with, well, if I think A causes B, let's see if they're related. Because if A causes B, they will be correlated. So, but if they're not correlated, okay, well then I was wrong. Let me look at something else. If they are correlated, now I can follow up my correlational study with an experimental study. Okay, some reasons you may not find a correlation even if there is a correlation. Restriction of range being a big one. Right? Whenever a correlation is computed from scores that don't represent the full range of possible values, you might be missing out. And it could be, in the example shown here, where if they had looked at all the values, you'd see, oh, that looks like a fairly linear trend, a positive correlation. But if they only get those kind of high-end values, and they don't see the ones down below, they see the blob, they go, no, there's no correlation here. Right? So if you're doing a study and you find, you get a troop of deployed soldiers, and you measure their combat exposure and some maybe symptoms of PTSD. And in that small sample, you find no correlation. Nope, no, it's not related. Well, it is related, but you're not going to find it in that group, partly because if they're in a troop together, they probably all have the same amount of combat exposure, and it's probably high, right? So if they're all high on this and potentially high on PTSD scores with some variability in there, you're not going to have a chance to see a correlation because you don't have the full range. You don't have those low scores on combat exposure to see what happens. Well, what happens when you have low exposure? I don't know. I only looked up here. If you only look in one area, then you're unlikely to see a relationship that's there. And again, and it's most often when you have restriction of range, that's what happens, where there is a relationship and you're not seeing it. Sometimes the opposite can happen, where you're looking, you're restricting your range and you get this kind of, you see a relationship, whereas if you look bigger, you'd see, oh no, it's not really there. But more often it's the former, where you're more likely to make a type 2 error with restriction of range than type 1. Flip side of that, outliers more likely to give you kind of a type 1 error, right? So outlier is a score that's really different, really smaller than or larger than all the other values. And there's all kinds of different rules for how different a score needs to be to call it an outlier. Oh, is it 1.5 standard deviations, 2 standard deviations? Is it in terms of standard error? Statisticians can fight about that. But the point is, it's weird scores. Like maybe somebody put in it's a coding error when they were entering the data. But the thing to note is it can lead to errant conclusions about correlations. So if we look at the data here, you've got these 1, 2, 3, 4, 5 data points on graph A. And if you just have those 5 data points, you get this correlation of R equals negative 0.08, pretty close to 0. That's not significant, it's a blob. Okay, look over in B, we got those same 5 data points, but then you got this one weirdo who had super high values on X, super high values on Y, and now that thing was far enough away from the rest of them that it drives this significant correlation. It goes from R equals pretty close to 0 to 0.85, getting pretty close to 1. So you really want to scan your data for outliers before running any kind of correlational analysis. And if you have outliers, you got to think about, okay, well, do I need to eliminate them? But you got to be careful about that. You can't just eliminate the outliers that don't fit your hypothesis. You have to have some kind of rule in place for which values you're going to eliminate from analysis. Okay, strength of relationship. Obviously, I've said before, the farther the correlation coefficient is from 0, the stronger relationship. But what's a strong correlation? It's relative. We're looking at like test-retest reliability. Those things need to be high, 0.8, 0.9. We're looking at, the correlation between scores on depression and scores on anxiety. Okay, 0.6, 0.7. We're looking at correlation between attitude towards something and the actual behavior. Okay, correlation of 0.3, 0.4. We found one of 0.6. Wow, that's huge. Okay. So what's a large correlation? Depends. So you have to look at the literature on whatever you're studying to say, okay, what size correlations are people typically reporting? And it's kind of like effect sizes. That'll tell you how relatively large your correlation coefficient is. Regardless of that, you can get something from the coefficient of determination, which is just squaring the R value. So calculate the correlation, multiply it by itself. That's the coefficient of determination. It tells you the proportion of variability in one variable that's systematically related to variability in the other variable. Right? Which we start doing the math on this, you think, okay, well, if two things have a correlation of 0.7, 0.7 seems like, oh, that's pretty good. It's a strong correlation. Yeah, well, square that's 0.49. That means it's 49%. About half of the variability in one variable can be explained by variability in the other. There's a whole other half that's not related systematically to that thing. Right? So anxiety and depression, if the correlation were 0.7, half of the differences in depression can be explained by anxiety, but then there's these other differences in depression where, okay, maybe usually people that are really anxious are really depressed. Yeah, but here's this person who's really anxious and they're not depressed, or they've been more depressed than we think they should be based on how anxious they are. There's some other variability in there that we can't account for with our knowledge of how anxious they are. Partial correlations. A partial correlation measures the relationship between two variables while controlling, statistically, the influence of a third variable by holding it constant. And typically you'll look at this if you're interested in two variables and you find maybe in your preliminary analysis that they're not correlated. Well, they sure should be. There must be something else going on here. There must be this third variable that's obscuring their relationship. And so you want to partial out that variance. You subtract it from the equation. So to do that, if you have, let's say, three variables, you could calculate a correlation between all three, right? R sub xy, relation between x and y, xz, and yz, right? So three different relationships between those three variables. If you did that, then the partial correlation between x and y holding z constant, so that's that notation r xy dot z, that means hold z constant, I'm going to partial out z, is the correlation between x and y, right? That's all that rxy is. It's not correlation of something times something, it's just the notation telling you which two variables it's the correlation coefficient for. So that correlation minus the correlation between x and z multiplied by the correlation between y and z over the square root of 1 minus the coefficient of determination for xz times 1 minus the coefficient of determination for yz. So again, you calculate the separate r values for each of those, and then you just plug it in, and that will give you the partial correlation, which tells you, okay, x and y are this much related after I account for any differences, any variability that is associated with differences in z, that third variable, right, which was maybe obscuring a relationship that I'm interested in. So when we calculate correlation coefficients, we don't have an R table like we had with ANOVA and t-test. So how do you do hypothesis testing? Well, you still have your null alternatives. So if you have a non-direction hypothesis, again, you state it at the parameter level, so it's rho. Then when the null is true, rho is equal to 0. Correlation is nothing in the population. Alternative, it's not nothing. Directional, so rho is less than or equal to 0, so it's negative or nothing. The alternative being that it's positive, or it could be the flip, right? To test that, to test if R is significantly different from 0, which is what the null is, you can use a t-test or an f-test, either way. And we'll look at doing a t-test. So the formula here is t is equal to r minus rho when the null is true, divided by this measure of standard error, which is 1 minus coefficient of determination, divided by your degrees of freedom, right? Because the degrees of freedom is n minus 2 for correlational analyses. And again, in the numerator, rho is 0 when the null is true. So really, that numerator is just your R value. So it's R divided by standard error. And the denominator is that standard error, where it's 1 minus the coefficient of determination. So the amount of variability you didn't account for, divided by degrees of freedom, square root that. And as I said, degrees of freedom is n minus 2. Again, where n is equal to number of pairs of scores. Other correlation coefficients, won't talk too much about. They all use the same formula as the Pearson. They're just for different types of data, right? Spearman's rho measures relation between variables on an ordinal scale. And sometimes you have variables that weren't originally measured on an ordinal scale, but you had wonky data, like they were really violated the assumptions of normality. You had some outliers. You said, okay, well, I don't want to have the misleading data, so I'm just going to turn all these into ranks. I'm going to rank order them, and then do a Spearman's rho instead of a Pearson's correlation coefficient. So that's one thing commonly done when you have, again, violations of normality or big outliers. The point biserial measures relation between two variables when one has numerical scores, but the second is dichotomous. Right? So if you had two groups, men and women, scores on a test, is gender related to scores on the test? You could count a point biserial correlation coefficient. I think, well, if I had two groups, wouldn't I just do a t-test? Yeah, you could. But the point biserial gives you something slightly different. The t-test tells you if there's a difference between the means that's statistically significant. The point biserial tells you if there's a significant relation between the two. And the one thing that it gives you the t doesn't quite so easily is it's much easier to calculate that coefficient of termination for a point biserial because you just square the R value. Whereas for the t-score, you have to go and calculate an effect size, and it's a few more steps. The phi correlation measures relation between two dichotomous variables, right? So if you had gender as a dichotomous variable, which it isn't necessarily, but if you had it that way, and you're looking at males versus females, and graduate versus undergraduate students, if there's a relationship between gender and class status on some variable, you could use a phi coefficient, but usually you're going to use a chi-square instead. Okay, so wrapping up. Correlations are all about direction and strength of relationships, right? Positive or negative, big, +1, -1, or small, close to 0. You cannot infer causation from correlation. You cannot infer causation from correlation, but it hints at it. And there are different types of correlation coefficients for different types of data. Typically, if it's not numerical, if it's ordinal or categorical, there's some other things you can use. Okay, that's all for now. Take care.